I'm happy to introduce our speaker, Professor Andrey Serebryany. Professor Serebryany did his PhD in a Marine Hydrophysical Institute in Sevastopol and his degree of Doctor of Science in the Acoustic Institute in Moscow and was in the Acoustic and Physical Oceanography. Andrey is principal scientist in Shear Institute of Oceanography of Russian Academy of Science and head of department of Andreyev Acoustic Institute. He worked as a visiting scientist at the University College, New Wales University, Canberra in Australia, and in the US in the Catholic University of America, Washington, D.C. and Woods Hole Oceanographic Institute. Professor Serebryany participated in more than 50 sea and oceanic expeditions, and he is an author of more than 250 scientific papers and papers in proceedings of the conferences. His research focuses on physical oceanography, geophysical hydrodynamics, acoustical oceanography, internal and nonlinear waves, and remote methods of exploration of hydrophysical processes in ocean. Please.
Thank you. So good afternoon to everybody. Title of my presentation is ADCP as a powerful tool of acoustical oceanography. ADCP is a acronym and Acoustic Doppler Current Profiler is acronym. So I work in Russia, in Russian Academy of Sciences with Oceanography, in Andrey Institute, etc., in Partial Time Space Research Institute. On this picture you see ADCP, one of type of this ADCP which we used in our experience, named Grande 600 kilogauss. During 4 seasons, firm Teledyne FD Instruments Europe supported our expedition work on shelves of Russian seas with free run of ADCP. And next slide you see my photo with director for the Instruments Europe, Mr. Hector Kyriatidis, during conference ADCPs in Action Europe, which was in NIDS France. And every year, specialists in ADCP participate in ADCPs in Action conference, which usually spent in San Diego, in the United States, and sometimes this conference organized in Europe. First of all, principles of operation of acoustic Doppler current profiler. The main principle is connected to so-called Doppler effect. Everybody knows who studied physics this effect, that if somebody listening some signals in standing position, frequency is 1, and if somebody moves to get to direction of sound transmitter, frequency became higher. And so this principle used in ADCP, and ADCP work in 2 regimes, transmitting and signals and receiving signals. So during transmitting signal, some backscatterers which are in Shear or in lakes, or in rivers, in water, and backscatterers is small particles which make backscattering or signal. And this backscattering signal in the moment of receiving signal is received by ADCP, but due to particles are not in usually exist some currents in the environmental medium, so particles is moving together with flow, and backscattering signal is changed, a frequency of the signal is changed due to Doppler effects, and this frequency receiving ADCP. ADCP usually have four beams, so it gives possibility to measure horizontal current in two components, east-west and north-south, as well due to beams are not perpendicular but inclined to horizon, so it gave possibility to measure third component of currents, up component of currents. This configuration is called so-called Yamas configuration, and the ADCP have possibility to measure current homogeneity due to if each beams have the same direction of flow, it's one situation, and sometimes if scales of measuring is so that some eddies exist and internal and currents propagate on this square different directions, so it's so-called inhomogeneity error, which calculate as well in ADCP. ADCP is possible used from stationary platform, but sometimes from vessels or moving boats. And you see four beams and this pass of both, and ADCP received signals from each horizons of this river on shelf zone of Shear, and collected data on three components of current. So what the ADCP measures: so velocity profile, flow homogeneity, range to bottom, vessel speed over ground, and echo intensity. So signal strength, echo intensity, it's have some information about processes in environmental media which we study. So ADCP have some special programs and that have possibility to see about many processes. For example, we can see average backscattering signal, trajectory of our profiles of backscattering signal, velocity magnitude in water column, up velocity, north velocity, east velocity component, and intensity signal, as well water speed relative to bottom. We have big experience in ADCP, so beginning from 2003 we carried out field experiments in 33 expeditions on shelves of the Black Sea and the Sea of Japan using ADCP of free ground. You see this Black Sea and position of our regions where our expedition was made. This is South Crimea, so Katsa Valley. This exists stationary oceanography platform from which we made our observations. This is Caucasus coast. It's Gelendzhik, not far from Novorossiysk. This is Russian territory, and this is region close to Sukhum. Now this is Abkhazia. Another regions when we used our ADCP in marine expedition is Far East, Sea of Japan, and this special scientific station of Pacific Oceanographic Institute of Russian Academy of Science, Beiritis and Schulz Cape. So this is the same coast of Russia. So in investigation of internal waves on shelf with using the superior ground gave us possibility to see the process in more detail. But we investigate not only internal waves but other process about which I will speak in close usage just now. So we use not only small boat with the DCP, but we used yacht. This example from Sea of Japan yacht. And smaller yacht we use in Black Sea. A stationary platform in Katsa Valley in Crimea. It gives possibility to make long-term observations on currents from here. So first of all, study currents on a ship. Due to Acoustical current profiler is an instrument or tool which used for the firstly for study currents. So this is example. Our trajectory of our small boat with the DCP, and this is some cross sections. No, one cross sections on which we see signal backscattering signal. Here, this is strong backscattering. This color about quite clear water, and this scale from here to here, it's decibels backscattering coefficient, and this is most velocity component in which we see strong currents in this part of cross section. So after a DCP survey we can present all systems of currents on this area which we study. So we see direction of input water to one direction, to this direction, and this currents to another direction. So this is subsurface currents. And next picture is bottom currents, so we can see on each horizon's situation with currents.
What is the water depth?
Water depth is from coast, from 0 to approximately 35 meters. So on this survey we can see not only direction of currents but as well distribution of backscattering signal on this equatorial. And backscattering is connected with existing condensed matter or phytoplankton in water. So approach of water from open shelf to the coastal water in time after storm in this picture. You can see, we can see that clear water back to coastal water, and after storm made mixing in this region, and this intrusion, first on front of this intrusion we see vertical displacement of these layers is connected with existence of trade on internal waves. So study sub-mesoscale ADs on a shelf. So mesoscale ADs is ADs with scales of 10, 15, 20 kilometers, which exist and generate in coastal water on Black Sea, not only Black Sea, of course, every seas. And this these eddies propagate to the northwest and and manifest itself as spirals on sea surface. So this eddy we met in this place, we made during 1 week sections from here to here with the ADCP on a boat, and we obtained this information. So first of all, this northwest direction of current, and before eddy and effect of eddy began work. Eddy in transaction in our position, you see this is from coast to approximately depth 30 meters. And we see direction change, direction in the opposite. So this currents became more stronger. This is back face of eddy, and next you see the eddy removed from our place of observation. During passing of these eddies, we see enhancing of currents in this eddy, and this situation gave possibility to see eddy through sea surface manifestation. Another effect connected with eddy is that the appearance of eddy lead to moving up position of thermocline, which we see here. At the before eddy and after eddy, we see the thermocline removed up to sea surface. So-called subsatellite measurements. So measurements which made during satellite make photo or radar images some regions of sea. During this moment we made satellite measurements from research vessels within the city. On this slide you see silicon sea surface connected with onshore concurrents in the Black Sea. So some process of hydrodynamics have manifestation on sea surface in the form of alone slicks or system of slicks, like in the form of spirals and etc. So this slick will generate due to situation with current in this position have one direction and this opposite direction, and in this place we met slick which was presented in previous slide. On this picture you see image of high recognition from radar SAT-2, and you see data of ADCP collected during satellite working in this region. We see that change of direction of current is coincide with slicks on this image, 1 and 2, etc. at here. So another possibility of ADCP is measurement of plankton distribution in this. So we can use ADCP like to which measurement plankton concentration, but it is necessary to make previously calibration. So calibration made, for example, is this ADCP picture obtained by us. In this place we made together with biologist standard station. On different horizons was collected probes of water, and after that biologists made by their methods determine concentration in phytoplankton, and after that we used for another sections of this region we used this data which was made calibrated, used data for DCP, and we can present distribution of plankton, vertical distribution of plankton to another points of shelf, using only DCP data. So internal waves are very good seen in ADCP reports. It's some examples. So this ADCP work like echo sounder, and you see that internal waves which close to the bottom have special form. It's connected with non-linearity of internal waves, but not only displacements of water we can see, so estimate heights of internal waves, but as well we collect another characteristics. This is north velocity component. Internal waves propagate to the shore, and we see that, like in internal waves, orbital currents is so that in bottom you see propagation particles of to the shore, and in opposite position propagate. The sea surface particles propagate in opposite position. So we see where internal waves is bigger, it's more prominent, this effect. And this is for the same picture, up velocity component. You see that, first of all, in internal waves, solitary waves, we see red color, which means that particles are moving up, and in back phase moving down. But again, surface manifestation of internal waves in the bay, you see, and this internal wave manifestation was generated by the process in thermocline. Sea surface here. Another examples of internal wave investigation in Far Eastern Sea of Japan. On this radar image we see several slicks, and this which good seen on this figure, and internal waves here propagate from this position to shore, and in this time we made measurements. We see internal waves in water column like sinusoidal form. This is solitary wave here, propagate to the shore. The solitary wave, internal waves in previous slide, produced the solitary slit on the surface. And it is possible to make estimation of the velocity of internal waves, made two transections to one position and in opposite position, collecting information from these two transections. We can very simply estimate internal wave velocity. So in this table you see that velocity of these solitary waves changed from this to this means. So internal waves propagate to the shore have more slowly velocity in shallow water. Non-linear effects in internal waves. So the horizontal asymmetry of internal waves. So in previous slides we see sinusoidal form. Sometimes when internal waves have big amplitude, so they became non-linear waves. So you see steepening of front face and flattening of back faces solitary wave. Here, this is measurements by ADCP. This measurements by temperature sensor contacted. So this effect collected by two methods. Another effect, so if the thermocline is close to the surface, so we have called elevation internal waves here. So sharpness crest of internal waves and flattened troughs. And when internal waves propagate in bottom shear, form of internal waves have form of depression waves. You see here. And in shallow water they became like elevation waves. So propagating from bottom to shore, from bottom region, from deep regions to the shore, internal waves must change its form in some place of shell. So this so-called effect of returning of internal wave of returning. On this picture you see coastal front generated due to strong storm in the Black Sea. So you see this is mixed water with big scattering, and this clear water from part of open sea, and this is sharp front. The sharp front accompanied by train of internal waves, propagation of front to the shore. Another interesting phenomena is so-called nonlinear internal wave bore. Bore is wave with very steep front, and this steep front manifests itself like approach of cold water from open sea. So you see strong enhancing of current in bottom layer, and this current propagating to the shore. Another bore is subsurface bore. So the same red color, it means that velocity is very high. No, you see up to 30 centimeters per second. This is the same for another example of internal bore in backscattering picture. You see the approach before bore, thermocline position not far from bottom, And after bore approach, we see like thermal line moved up, up to 5 to 10 meters. Observation of stationary platform in the Black Sea. This color, red color, means that a lot of basketing was laid on thermal line. But when thermal line was moving up, scattering this means zooplankton decided that it's not convenient position and disappeared here. So it's possible to study processes responsible for generation internal waves in the sea. This is one of examples. The same measurements in the Sea of Japan. We met interesting effect when tidal currents propagate to the shore, met with a long shore current, and in point of meeting a long shore current with tidal waves, it's this place generation of intense internal waves took place. The same we made section with ADCP on yacht, and this transaction we obtained this data of ADCP. We see position along shore current, and this is position of current due to ebb. This is temperature distribution of this region, and this we see like in this place we see appearance of internal waves, trains of strong, of big amplitudes, which propagate to the shore. Internal waves exist not in open ocean, in open sea. Usually generation internal waves connected with tide, but in so closed sea like Black Sea, internal waves exist as well, and they generation connected with another process. Sorry for Russian description of this picture, but I will say that the example of internal waves observation in Black Sea, and in Black Sea sometimes we can see enough intense internal waves. You see that this height of these waves up to 10 meters, in position of depth only 40 meters. So it's again non-linear internal waves. Another example is internal waves connected with moving of ship. So it's artificial internal waves, not nature generated. You see, this is internal waves was made by moving vessel. But this another example connected with elemental and very natural source internal waves. So strong seritons, 1, 2, 3 in this train, propagate to the shore. And on this picture we see that strong up currents, red and purple color. It's red moving water up, purple water down, and periodically it's dry. Another interesting effect of shear instability, which can be absorbed in coastal water as well. Again, we see on sea surface some slip, but generation of slicks sometimes connected with different mechanisms of generation. This mechanism connected with shear instability. So, after our observation with ADCP, we revealed that this leak was connected with this position, and this is backscattering signal. We can see 5 billows with heights up to 10 meters propagated here, and these billows are generated by very strong shear current here. This is velocity magnitude. Strong opposite current 30 centimeters per cent beneath position of thermocline was observed here. So strong current propagate here, and this propagate in opposite position. Other important effects connected with internal waves. This effect of internal waves on subsurface layer of air bubbles in the sea. So there are existing in the sea subsurface bubble layers, which can thickness of which may modify by passing internal waves. So we see internal waves. This is concentration of bubbles, and we see that on this front face we see concentration bigger and thickness is bigger of this layer, and on back face of this wave we see that thickness is smaller. It's the same for another wave. Again, thickness is bigger and dissipated practically. So this explanation of this effect is connected with the effect of orbital currents with of internal waves. So we see that internal waves have currents which moved here and here, and so this is so-called divergence zone. In divergence zones, thickness is again smaller, and in convergence zone, when currents concentrate bubbles, so thickness became bigger. So it's interesting to see so-called interthermocline lenses. Lenses exist in ocean, and lenses exist in, for example, in Atlantic Ocean, so-called Mediterranean lenses, well known. But on shelf, sometimes we can see lenses as well, and it's a bigger possibility to see clear thing. You see, this is lens from here to here, approximately 3 kilometers. Yes, length, and we see that in center pole lenses more scale is bigger here, and we see that some form like sinusoid form is connected with, through this lens, propagates some internal waves, and it's clear seen on this picture. Especially good seen it's during time of night. Another interesting effect which we can see using ADCP, it is a form of relief. And in this example you see the relief of bottom, very like remind us form of solitons, which trains of internal solitons. So internal solitons propagate from here, met with this seal, and working so that generate and transform relief in the form of dual solitons. By the way, this picture was included in monograph Shallow Acoustics of Katznelson, etc. That's the conclusion. So ADCP Grande demonstrated itself as a powerful and conventional tool of acoustical oceanography. It gave possibility to collect valuable data, essentially approach us in understanding the processes on the sail show. So thank you for your attention.